We just detected the largest sunspot seen in a decade. But here's the terrifying truth. Last week, 6,000 jetliners were grounded after a single solar particle flipped a bit inside the autopilot of a JetBlue flight. Are the skies safe? If that small particle costs billions, what happens when the inevitable superstorm melts the backbone of the $2 trillion global power grid?
Today, December 1st, 2025, space weather has officially crossed the line from, theoretical science into an immediate breaking global emergency.
And that's not hyperbole. For decades, experts have warned about this once-in-a-century solar superstorm.
Right.
But right now, we are in the middle of a very intense solar maximum, and the evidence suggests that the threat isn't just imminent. It's already actively destroying our technology.
Exactly. The source material is screaming. We have identified a monster on the face of the sun. Active region, or AR, 429P496.
And this thing it's visually staggering.
It's clocking in at over 10 times the size of Earth. And just in the past few hours, it erupted. It unleashed an X1.9 class solar flare.
That is the most powerful designation possible, the top of the scale.
The electromagnetic pulse from that flare is already here. It hit the upper atmosphere at the speed of light.
Which gives us, 8 minutes of warning for those specific effects? But the core danger, the real threat, is what's following it.
The blob.
The massive blob of energized plasma, the coronal mass ejection, and it is screaming its way right toward us.
And here's the real gut punch, the thing that makes this deep dive so urgent. This isn't a problem for the future anymore.
No.
Just weeks ago, a smaller, almost innocuous solar event caused a real-world, multi-billion-dollar systemic crisis. We are talking about a $2 trillion disaster potential.
Thousands of grounded Airbus planes.
And the chilling realization that our entire digital world is, it's built on sand.
You tasked us with figuring out how a ball of gas 93 million miles away could functionally end our digital age.
Yeah, how does that even work?
How do particles from space crash an airplane, melt multi-ton power transformers, and functionally silence the global internet? So we're taking your sources and we're going to unpack the true mechanics of the grid killer.
The internet apocalypse.
And the sheer devastating vulnerability of the space catastrophe that this solar cycle has just laid bare. We have to understand not just what happens, but how the physics of the sun interacts with our infrastructure to create this level of failure.
Okay, let's unpack this immediately. Starting with the story that proves this isn't theoretical. The solar storm is already here.
It is.
We're talking about the JetBlue Flight 1230 incident, October 30th, 2025. This Airbus A320 was just cruising, Cancun to Newark, autopilot engaged, everything is normal.
And then complete uncommanded chaos.
What happened?
The aircraft suffered a violent, uncommanded nose-down pitch event. And this wasn't a slow drift, It was abrupt.
A sudden lurch.
Exactly. The pilots were fighting the controls as the plane dropped 26,000 feet in just 10 minutes.
26,000 feet.
The G-forces were significant enough to throw passengers and crew all around the cabin. It resulted in 15 to 20 injuries before the pilots finally managed to wrestle the aircraft back under control and divert to Tampa.
It was a terrifying, near-fatal event, and the cause is where this whole story just gets so deep.
Because it wasn't a mechanical fault.
Right. Not turbulence, not pilot error.
No. The forensic investigation pointed the finger straight at the sun, specifically solar particle radiation causing a bit flip.
A bit flip? This sounds so small.
It is, and that's what's so scary. This is where we have to dive into the microphysics. When the sun spits out these energetic particles, they travel through space. When they hit Earth, they collide with atoms in our atmosphere.
Nitrogen, oxygen.
Right, the nuclei. And they cause a process called spallation. This collision creates a shower of secondary high-speed subatomic particles, mostly neutrons.
And these neutrons can just rain down into the lower atmosphere.
It can, right down to cruising altitude. A neutron is neutral, so it doesn't get deflected by the Earth's magnetic field easily.
Which makes it a perfect digital assassin.
Precisely. And when that high-speed invisible neutron hits a microscopic memory cell on a critical computer chip, in this case, the elevator aileron computer, or ELACB L104, it transfers its energy.
It just slams right into it.
It causes a localized ionization event, a sudden surge of electric charge in the silicon.
And silicon is what stores our digital information as a 0 or a 1. So it suddenly gets this jolt of charge it wasn't expecting.
And that surge is enough to flip the state. A stored data bit, which should have been a 0, spontaneously changes to a 1. or vice versa.
That's the single event upset.
That's it. And in the case of the Airbus, that one rogue particle hitting that one specific microchip caused the entire system to generate an erroneous pitch command. It told the nose to aggressively dip down, completely overriding the autopilot.
It is utterly staggering. The difference between a routine flight and a crash can come down to a single atom of silicon being struck by a secondary neutron that was generated 93 million miles away.
And the regulatory response shows they know this wasn't a fluke. It was a systemic vulnerability they had to address immediately.
The response was swift and globally binding. EASA, the FAA, they issued Emergency Airworthiness Directives, EADs,
requiring modification or replacement of those affected ELT units before the next flight.
Think about the economic scale of this. This single incident led to the grounding of between 5,900 and 6,200 Airbus A320 family jets globally.
That is the largest single-model grounding we've seen since the 737 MAX crisis.
It wasn't just inconveniencing a few airlines. This was a fundamental supply chain nightmare. I mean, Indigo, a massive operator, had 68% of its fleet offline.
And that's where the economic insight gets really deep when you look at the cost. Our sources estimate the total global impact lands somewhere between $3.5 and $4.5 billion.
Billion with a B.
Yes. And that's factoring in everything. The cost of fleet-wide modification, emergency logistics, and crucially, the massive revenue loss from all those grounded flights.
For major carriers all over the world.
And it's not just the hardware cost, it's the immediate paralysis of the entire global aviation network.
And that $3.5 to $4.5 billion wasn't caused by a Carrington-level superstorm. This was a relatively minor high-intensity burst of solar radiation.
One that was just strong enough to penetrate our defenses.
So if a small event causes a multi-billion-dollar fleet-wide disaster today, what happens when the actual predicted once-in-a-century superstorm finally arrives?
To even begin to answer that, we have to calibrate our understanding of the risk by looking back at the benchmark of doom. We need to go back to a time when our technology was simple, but it still failed catastrophically.
The Carrington Event.
To truly grasp the stakes, we have to travel back to September 1859. This is the moment Richard Carrington, a British amateur astronomer, observed an intensely bright white light erupting from the sun. What followed was the superstorm.
And it remains the measuring stick for solar intensity.
Absolutely.
The accounts from that era sound beautiful, but also completely terrifyingly alien.
They were awe-inspiring, and for a population that didn't understand the mechanisms, deeply confusing. The geomagnetic storm that resulted was so powerful that auroras, the northern lights, were seen globally.
Far outside the polar regions.
Way outside. Imagine stepping outside in the middle of the night in Cuba, or the Caribbean, or down in Sicily, and seeing the sky just blazing red and green. People woke up thinking their cities were on fire.
That visualization, the sky lit up over Havana, perfectly conveys the raw, unbridled energy hitting the Earth's magnetic field.
And while the visual spectacle was dramatic, the technological chaos was proof of the storm's inherent destructive capacity.
Right, because the only long-distance electrical communication they had at the time was the telegraph system.
The brand new, nascent telegraph system. And it was just decimated.
So let's focus on the human factor here. What did the telegraph operators actually experience? What did they see?
The sources recount operators getting these painful, debilitating electrical shocks right through their equipment. Sparks were literally flying off the machines.
Wow.
And the paper they were using to transmit the messages, actually caught fire in several stations.
So the system was on fire.
And some operators realized they didn't even need to connect their batteries anymore. The wires themselves were carrying this massive rogue current induced by the solar storm.
So the whole system was generating its own power.
In a totally destructive way. And that is the crucial connection. Those 1859 copper wires were carrying geomagnetically induced currents GICs.
The very same phenomenon we're worried about today.
Exactly. But now it's magnified, 10,000 times by our high voltage grids.
And the scale of our modern vulnerability is why the numbers are just so shocking. The National Academy of Sciences did a study on this.
They estimated the impact of a Carrington magnitude event hitting our complex, interdependent infrastructure today.
And what was the economic cost?
A total economic damage exceeding $2 trillion.
$2 trillion? That number is so large it just becomes abstract.
It does. So let's unpack what that really means. Because a knowledgeable audience member might immediately ask, does that just cover replacing the broken stuff?
Right. If the grid is down for a year, the lost GDP is going to be way more than just the cost of a few melted transformers.
Exactly. And that's why the 2 trillion figure is actually conservative.
Yeah.
It tries to account for everything. A, the direct asset replacement cost, the thousands of custom transformers that are destroyed.
Okay.
B, the lost GDP during the recovery period, because transportation, financial markets, manufacturing, it all just stops.
And C,
The secondary damages, food spoilage, water system failure, civil disruption. It is 20 times the cost of a disaster like Hurricane Katrina, and that's just the immediate aftermath.
And the chilling part is that this isn't just some historical event from 1859. We had a modern dress rehearsal that we barely survived.
The July 2012 near miss.
Tell me about this.
NASA confirmed that the coronal mass ejection that erupted then was, and I quote, in all respects at least as strong as the 1859 Carrington event.
So it was another Carrington.
It was. The ultimate bullet dodged. Because Earth was literally just 10 days further along in its orbit, the storm missed us entirely.
We were blissfully ignorant.
That's what the scientists said. We had no idea how close we came to launching the digital age right back into the 19th century.
Oblivious to a $2 trillion loss. That brings us to the statistical probability calculated by Pete Riley.
Right, in the journal Space Weather. Riley calculated the probability of a Carrington-class storm hitting Earth in the next 10 years.
And the result?
It was a 12% chance.
12%. That doesn't sound huge, but over time.
But when you translate that into a recurrence interval, it suggests that these events happen, on average, every 79 years.
But the critical warning here, the whole when, not if thing, is that these are random events.
They do not adhere to a nice, predictable 79-year cycle. Probability dictates that we could wait 300 years for the next one. Or, crucially, we could get hit tomorrow.
We got missed in 2012. We could be hit in 2026.
The danger is nonlinear, and our incredibly fragile aging infrastructure is just sitting right in the crosshairs.
The 1859 storm had only copper wires to burn. Our world is built on 3 hyper-vulnerable systems: the power grid, the internet, and our satellites.
And we have to start with the one that affects everything else: electricity.
So let's get technical, but keep it simple. When a massive CME hits Earth's magnetic field, how does that magnetic energy turn into an electrical current, the GIC that melts things on the ground?
The fundamental concept is electromagnetic induction. When the CME slams into the magnetosphere, it makes the Earth's magnetic field shake, and shake rapidly.
And a rapidly changing magnetic field.
It induces an electric field. And because the Earth's crust is somewhat conductive, especially where it's wet or mineral-rich, that electric field generates electrical currents within the ground itself.
Those are our geomagnetically induced currents, the GICs.
Those are the GICs, and the grid acts as the perfect victim.
So use the giant antenna analogy to explain how this GIC gets from the ground into the power lines.
Okay, think of our high-voltage power lines and all their grounding points as a vast, interconnected, and extremely long antenna system.
Spanning whole continents.
Exactly. The GICs flowing through the ground are basically just trying to find the path of least resistance to dissipate. And that pathway is any extremely long conductor connected to the Earth.
Which is the entire high-voltage power grid.
The entire system is effectively soaked in rogue, unwanted, induced DC electricity.
It's like pouring the wrong kind of fuel into a highly specialized engine. And where does this unwanted tidal wave of electricity rush into?
It rushes right into the weakest link, the one component that is utterly intolerant of DC current.
The transformers.
The high-voltage step-up and step-down transformers. These are the custom-built, multi-ton supergrid transformers, or SGTs, that are the absolute foundation of long-distance power transmission.
Okay, so why are transformers, which handle massive AC power all day long, so vulnerable to this solar-induced DC current?
Because they're designed for alternating current. AC relies on the continuous flipping of the magnetic field in the transformer core.
Back and forth, back and forth.
Right. When this quasi-DC current from the GIC gets introduced, it pushes that magnetic field off-center. It forces the core into what engineers call half-cycle saturation.
And what does that physically mean? What happens inside the transformer when it saturates?
When the core saturates, it can't contain the magnetic flux efficiently anymore. The magnetic field leaks out, and that causes extreme rapid heating inside the transformer windings and the steel core itself. You get these localized hotspots.
And things start to melt.
The heat is so intense that the copper windings can melt catastrophically. Or the insulating oil degrades violently, leading to alarm shutdowns, or worse, an explosion.
The damage is irreversible.
Completely. It renders the transformer useless. a total write-off.
And here's where the deeper technical insight comes in. Not all transformers fail the same way, right? The design matters.
That's a critical point for policy and utility investment.
Mm-hmm.
Most older or high-capacity U.S. transformers use what's called a 5-limb core. They're incredibly efficient for AC.
But terrible for GICs.
Highly susceptible. When GICs push the flux into saturation, those 5-limb designs are easily overloaded.
But the UK and some other European systems are moving towards a different design.
Yes, the 3-limb core transformer. This design, while maybe a little less optimized for AC efficiency, is significantly more resilient to GICs. The core structure itself helps mitigate the effects of the DC current.
So it's a design choice. You can build a more robust grid.
Absolutely. GIC mitigation isn't just about putting up shields. It's about making smarter, more resilient design choices from the start.
But regardless of the design, if enough of these custom units are damaged, the entire grid fails. And the recovery challenge is just brutal.
It is the non-negotiable roadblock. Damaged SGTs are not mass-produced. They are custom-built, they weigh hundreds of tons, and they require a specialized, very limited manufacturing capacity.
So how long does it take to replace one?
Sources indicate that replacing a single unit, and this is assuming the global supply chain is even still functioning, takes 12 to 18 months, often longer.
So a severe GIC event means months, possibly years, of widespread, sustained blackouts.
Across large swaths of the planet.
Yes. And this isn't just a theory. The 1989 Quebec blackout is the famous casualty.
That was the classic modern case. A severe GIC event caused a 9-hour outage of Hydro-Quebec's system, disrupting 6 million people and causing about $6 billion in losses.
But we also saw real-world stress just recently.
The 2023 CME storm.
Right.
In April 2023, a coronal mass ejection had this really powerful density pulse. And GIC measurements taken across Finland, Canada, and the U.S. upper Midwest revealed currents that were comparable to the maximum readings seen in those regions over the last 15 to 25 years.
So even a medium-sized event is enough to push the system to its limits.
It confirms that our current infrastructure is being stress-tested constantly.
Okay, so if the power grid is down for months, no refrigeration, no fuel pumps, no connectivity, what happens to the internet? We often think of the internet as this ethereal cloud, but it's all physical.
And the cascading failure is absolute. No power means no local internet, obviously, but the core threat is a global communication failure.
Let's clarify a crucial fact for everyone listening. 99% of all global internet traffic flows through physical cables laid on the ocean floor.
Correct. The fiber optic glass itself is non-conductive. It's immune to electrical current. So you might think, oh, the system is safe. But the system relies entirely on maintaining that signal over vast distances.
Which brings us to the vulnerability. The repeaters.
Every 50 to 100 kilometers along a transoceanic cable, there has to be a repeater. It's a specialized signal booster, just to make sure the data stream doesn't fade into digital silence.
And these repeaters are electronic devices. They need power.
They do. And they're powered by thick copper sheaths that run the entire length of the cable, carrying DC voltage that can be up to 10,000 volts.
So now we have another huge, long conductor, potentially thousands of miles long, stretching across the ocean floor.
And that conductor is sitting in a giant pool of salt water and sediment, which is an electrical conductor.
So just like the power lines on land.
Massive geomagnetically induced currents flow through the conductive seawater and the ocean floor and slam right into the copper power sheets of these submarine cables.
Which means the GIC current attempts to overload or physically fry the electronic repeaters.
If that GIC surge is strong enough, those repeaters fail. And if enough major transoceanic lines, the arteries connecting North America to Europe or Asia to the US, are severed, you don't just lose speed.
You face a true internet apocalypse.
Continents become functionally isolated. Regions would have to rely only on their own national or continental networks. Global financial transactions, multinational corporations, international governments, they would all be severed for months.
The isolation and the global financial freeze that would cause is terrifying. But the digital catastrophe isn't limited to communication. We also lose our ability to know where we are, or even when we are.
The loss of reliable global navigation satellite systems, GNSS, which includes GPS, is the second major digital fallout.
And GPS is critical for so much more than just finding your way to the grocery store.
It's precise timing. Every financial transaction, every cell tower synchronization, every drone operation, it all relies on that exact timing signal from GPS.
And the mechanism of failure here isn't GIC, it's atmospheric distortion.
Exactly. We can explain it with an analogy. Plasma potholes.
Okay.
The GPS radio signals have to travel through the ionosphere, a layer of the atmosphere that's usually charged with plasma. It's a relatively smooth, predictable highway for radio waves.
But a solar storm fundamentally changes that highway.
It superheats the upper atmosphere, causing massive energy fluctuations. And this creates intense, low plasma density voids. Sometimes they're called bubble-like ionospheric superdepletion structures, or BLIS.
The plasma potholes.
Those are the potholes.
So what happens when a highly precise GPS signal hits one of these potholes?
It causes a disruptive effect called scintillation. Yeah, imagine looking at a star that's twinkling aggressively. That's light scintillation. For a radio signal, it means the signal gets scattered, refracted, and delayed. The distortion is so significant that the GPS receiver on the ground or in an aircraft becomes severely confused.
It can't calculate its position accurately.
It can't. So instead of an accurate location, you get GPS ghosting. You get huge positional errors. Planes, military assets, self-driving vehicles, they could be told they're miles away from where they actually are.
And the timing signal gets compromised.
The precise timing signal, the lifeblood of modern finance, could be knocked out. Experts estimate a superstorm could render GNSS partially or completely unreliable for anywhere from 1 to 3 days.
And in that window, the global economy just grinds to a halt.
So the sun hits us with two distinct weapons. You've got the electromagnetic induction, the GICs, to destroy the power and internet backbone.
And then you have the particle and energy flux to destroy our timing and navigation systems like GPS.
And if these systems are failing on the ground, we have to look at the first victims. The thousands of satellites we rely on up in orbit.
Which are the first things to get hit.
Absolutely. The data suggests that our space hardware is essentially defenseless against the worst-case scenario.
Hold on just a second. We just connected an atomic-level physics concept, a bit flip, to the grounding of 6,000 jets.
Right.
And then pivoted to the idea that massive currents are literally seeking out our transoceanic internet repeaters under the sea. I mean, the detail you are pulling from these sources is truly electrifying.
Well, thank you. That's what a deep dive is all about, right? We want to take these dense, highly technical papers and just give you, the listener, the ultimate cheat sheet.
The aha moment.
Exactly. The moment that connects seemingly unrelated disasters, like an airline pitch event and a melted power grid, to the very same source.
It truly is the intellectual shortcut to being thoroughly informed. And if you are enjoying this mind-blowing journey through the imminent solar threat, then please take a moment.
Please do.
Hit that like and subscribe button. Seriously, the more support we get, the more we can commit to finding and explaining these vital, surprising facts.
And join our memberships. We provide access to the raw source material, and your support helps us fund the investigative deep dives that bring this level of comprehensive, synthesized knowledge straight to you. We love that your curiosity fuels our mission.
Absolutely. Now, let's go where the sun hits first. What happens to the billions of dollars of hardware we have circling the Earth? Let's plunge into the space catastrophe.
Okay, space is the front line. And when it comes to the extreme events we are modeling, Carrington-level or worse, the conclusion drawn by experts is chillingly simple.
Which is?
There is no defense.
Let's discuss the ESA simulation. That's Europe's most severe space weather drill. What did they model, and what was the consensus?
The European Space Agency ran simulations modeling a hypothetical but plausible extreme event, an X-45 class flare.
X-45. To put that in perspective, that's roughly 25 times more powerful than the X-1.9 flare we saw today.
It's a monster. And the conclusion from the engineering experts who ran the drill was stark. No spacecraft would survive a storm of that magnitude.
No spacecraft.
It means all electronic communication, all satellite-based navigation would be entirely wiped out.
That's functionally the end of the space-age fleet in orbit. But we don't even need an X-45 flare to cause massive losses. We saw real modern-day destruction from a relatively common solar event just recently.
The February 2022 Starlink drag disaster. This is the key modern case study. SpaceX launched 49 new Starlink satellites.
And within days.
40 of them were immediately lost. They didn't collide. They didn't suffer an EMP strike. They simply fell out of the sky.
So what was the physical mechanism? What caused these multi-million-dollar satellites to just decelerate so quickly?
It was extreme atmospheric drag.
Drag.
When the solar storm hit, the high-latitude energy, all those protons and electrons flowing down the magnetic field lines, significantly heated the Earth's upper atmosphere, specifically the thermosphere, which is that thin layer where low Earth orbit satellites, LEO satellites, typically operate.
So heating the atmosphere changes its physics?
Exactly. The energy influx drastically enhanced the thermospheric neutral density by up to 150%. Think of the atmosphere in LEO as normally being a feather-light haze.
Right, almost a vacuum.
When it gets heated, it becomes significantly denser. It feels like thick mud to a satellite trying to maintain orbital velocity.
They encountered so much drag that they just slowed down past the critical point.
They slowed down rapidly until gravity won. They began an irreversible, fiery re-entry.
Wow.
The disaster highlighted the extreme vulnerability of these LEO mega-constellations. Even a moderate solar storm can create an atmosphere dense enough to effectively wipe out a freshly launched fleet.
Which forced Starlink to change its procedures.
Right. They had to adjust their operational procedures post-launch to account for this drag risk.
Now, for the satellites that are flying higher, or the ones that manage to survive the drag, they still have to face that direct particle bombardment we talked about with the Airbus jet. What does that long-term radiation exposure do?
It causes two types of chronic damage that accelerate aging dramatically. First, you have the single event effects again, the Cs.
The bit flips.
Exactly. These are high-energy protons and electrons that penetrate the satellite shielding and hit the chips. They cause both soft errors, transient data corruption that can be corrected, and hard errors.
Which are permanent.
Permanent device burnouts, effectively killing an instrument or a subsystem for good.
And the second type of damage is the cumulative, invisible aging process.
That's the cumulative dose. Satellites that survive the initial blast and the drag will experience severe, rapid performance degradation. The constant bombardment of high-energy particles causes the total absorbed radiation dose to just spike.
So what does that look like in practice?
Engineers describe the phenomenon as surviving satellites appearing to age several years in only a few days. Their operational lifespan is severely shortened, potentially making them useless long before their designed mission life is supposed to end.
So we have multiple points of failure. The sun can melt the grid, sever the internet, blind the GPS, and destroy the entire fleet of hardware orbiting the planet through drag, heat, and direct particle bombardment.
It's an all-out assault.
So, given this overwhelming inevitability, the 12% chance in 10 years, and today's massive sunspot, what actionable preparedness measures are being taken by governments, and what can individuals realistically do?
Let's start with the most critical factor, which is warning time. How much of a heads up do we actually get before a major solar punch hits?
It depends on what part of the storm you're talking about, right?
Exactly. The warning time depends entirely on the component. If we're talking about the high-energy solar flare, the pulse of X-rays and gamma rays, that travels at the speed of light.
We get 8 minutes.
Just 8 minutes notice. That's enough time for operators to confirm an impact is happening, but it's insufficient for any meaningful mitigation.
You can't start shutting down multi-state grids in 8 minutes.
Absolutely not. However, the coronal mass ejection, the CME, the massive plasma cloud that carries the GIC threat, that travels much slower.
How much slower?
CMEs typically take 1 to 4 days to reach Earth. But here is the major caveat.
There's always a catch.
We only gain certainty about the CME's trajectory and, crucially, its magnetic orientation.
Which determines how destructive it will be.
Right. We only get that crucial data when it hits the L1 point.
That's the Lagrange point between the Sun and Earth, where our sentinel satellites like ACE and Diascovi are sit.
Correct. And when the plasma cloud hits L1, we get an actionable warning window of only 15 to 30 minutes before that CME hits Earth.
15 to 30 minutes, that's it.
That narrow window is the most valuable intelligence we currently possess for mitigation.
That knowledge has to be driving international cooperation. This isn't just a domestic threat, it requires global monitoring.
Which is why future missions are so critical. The international community is investing heavily in improving that narrow window. The most prominent effort is the Vigil mission.
Scheduled for deployment around 2031.
Right. Vigil is designed to orbit at a different position, outside the typical Sun-Earth line. It will give us a vital side-on view of CMEs as they travel.
Which should improve our forecasts.
Significantly. It should improve trajectory modeling and magnetic field forecasting, increasing our actionable warning time from minutes to, hopefully, hours.
So in terms of protecting the infrastructure we have now, with that 15 to 30-minute warning, what specific protocols do utility companies have in place to try and save their transformers?
They have highly detailed emergency procedures. The most immediate protocol is load shedding.
Intentionally reducing the load on the grid.
and potentially intentional disconnection of certain high-risk, long transmission lines, often in the northern latitudes where the GIC threat is highest. By reducing the overall current in the system, they lower the magnitude of the GICs that can enter those critical transformers.
And if that fails, what about the replacement strategy? You mentioned the UK National Grid holding spare transformers.
The UK National Grid is one of the more proactive operators. They've increased their spare transformer holdings, and they're focusing specifically on those GIC-resilient 3-limb core units.
Over the vulnerable 5-limb designs.
Exactly. But their procedures estimate that even with a spare immediately available, the specialized transport and installation of a multi-ton transformer still takes between 8 and 16 weeks.
And that's if everything goes right.
The key bottleneck is logistics moving these massive units across national infrastructure, doing what is simultaneously a massive national disaster.
Now let's pivot to the crucial discussion for individuals, because there's so much confusion between solar events and military threats. We need to clearly contrast geomagnetically induced currents with a high-altitude electromagnetic pulse, an EMP.
This distinction is paramount. A high-altitude EMP is from a nuclear warhead detonating far above Earth. It generates an extremely fast, high-frequency pulse that can overwhelm and destroy small, delicate microelectronics directly.
Even if they're turned off?
Often, yes. Even if they're turned off, but connected to small traces of wires that act as antennas.
But a Carrington-level CME event is GIC-driven. It's different physics.
Completely different. GICs are slow, low-frequency, quasi-DC surges. They primarily affect long conductors.
The miles of power lines, oil pipelines, communication cables.
Right, because the physics of induction requires that large surface area. They generally bypass the internal microcircuitry of small, localized devices.
So the widespread fear that a CME will fry every cell phone, every laptop, every modern car is scientifically inaccurate.
Largely, yes. The consensus is that small electronics, your laptop, your phone, a battery-operated radio, are significantly safer if they are unplugged from the vulnerable grid.
The danger comes from being physically connected to that long conductor pathway.
Like being plugged into a wall outlet during the surge.
Yes. This also means that those common surge protectors people have are utterly useless against a GIC threat.
They are completely ineffective. A surge protector is designed to clip a high-voltage AC spike that lasts for milliseconds. GICs are slow-moving, massive DC currents that overwhelm that protection mechanism for sustained minutes.
You can't fight the entire planet's induced current with a little box from the hardware store.
You cannot.
And for sensitive, critical electronic devices, the simple solution of the Faraday cage remains the most recommended low-cost mitigation.
Absolutely. A Faraday cage, which is really just a conductive metal container like a metal trash can with a tight lid, provides an effective shield against that electromagnetic radiation. It protects sensitive, unplugged electronics during the initial pulse.
But let's contextualize the preparation here.
Right, the larger reality.
The ultimate preparation for a Carrington-level event has to acknowledge that if the grid is down for months or years across entire continents, the challenge shifts from protecting your phone to ensuring long-term survival.
You're preparing for a scenario where transportation stops because the fuel pumps are all electric. Water purification fails. Critical supply chains for food and medicine just break down.
This moves way beyond a technology problem and becomes a fundamental societal resilience challenge.
It forces us to confront the fact that modern civilization, particularly in densely populated urban areas, operates on an extremely narrow margin of error. If you can't operate refrigeration, power financial transactions, or pump water, the cascading failures quickly move from digital inconvenience to an existential threat.
This deep dive has truly taken us on an incredible and, well, slightly unsettling journey. From a single particle causing a near-fatal aviation incident just weeks ago, to the monumental threat posed by today's X1.9 flare and that monster sunspot.
We established the historical benchmark of the 1859 Carrington Event. We've detailed the core physics behind the geomagnetically induced currents that melt transformers.
And we established the dual digital threat to the internet's submarine cable repeaters and the GPS signals compromised by atmospheric plasma potholes.
And we wrapped with the stunning vulnerability of our space assets, confirmed by that ESA simulation that predicts no spacecraft would survive a true superstorm, and the very real loss of 40 Starlink satellites to atmospheric drag.
The threats are multiple, systemic, and statistically probable, a 12% chance in the next decade.
Which brings us to our final, deepest question for you, the listener. We focus entirely on X-class solar flares, which are the most powerful in our current scale.
But the universe holds much, much more destructive potential.
You're talking about the theoretical possibility of solar superflares.
Exactly. Astrophysical studies suggest that our sun, like other stars, is capable of producing superflares. These are eruptions that could release energy up to 1,000 times greater than the 1859 Carrington Event.
And these are often modeled using data from other stars because we haven't witnessed one on our own sun in the modern age.
So here's the thought.
If the Carrington Event, which nearly happened again in 2012, is our benchmark of doom, and it nearly wiped out our foundational infrastructure, how close are we, statistically, to the ultimate space weather catastrophe? And how much longer can our increasingly complex and brittle global infrastructure withstand the inevitable barrage of solar punches?
A question to ponder as you think about which electronics you might need to unplug tonight. Thank you for joining us for this deep dive into the Carrington calamity.
We'll see you next time.